For 165 years, Kirchhoff's law of thermal radiation was a bedrock of physics. An object's ability to absorb energy must equal its ability to emit it. This principle, called reciprocity, shaped everything from telescopes to our understanding of stars. But in July 2025, scientists at Penn State University shattered this unbreakable law. They engineered a material that could absorb more energy than it emits, or vice versa, demonstrating non-reciprocal thermal radiation once thought impossible. Imagine a one-way street for heat energy can travel in, but not easily escape. For over a century, physics insisted this street had to be two-way. By breaking this balance, the researchers unlocked a new dimension of control over heat. This isn't just academic, it could spark a new era of innovation. The discovery challenges a core assumption that underpinned countless inventions. If a law held certain for 165 years can be overturned, what else might we need to re-examine? This is more than a scientific paper, it's a testament to human ingenuity and our relentless quest to understand the cosmos. We've just turned a thrilling, unexpected page in the book of nature. To grasp the magnitude of this achievement, let's revisit Kirchhoff's law. Gustav Kirchhoff's 1859 law said a material's ability to absorb and emit energy at a given wavelength and angle must be equal. This symmetry explained why black objects heat up and shiny ones stay cool. The Penn State team, led by Alireza Kalantari-Dehagi and Zhenong Zhang, dared to break this symmetry. They created a material that could listen intently but only whisper back, or vice versa. Their experiments showed a non-reciprocity contrast of 0.43, where classical physics demanded zero. This is not a small error, it's a clear, massive violation of the old law. It proves we can design materials with fundamentally different absorption and emission properties. This breakthrough shifts thermal radiation from a passive property to an active, designable feature. We're no longer bound by reciprocity, opening a new frontier in material science. Now we can tailor materials to manage heat in ways once thought impossible. This is the dawn of a new paradigm in thermal physics. How did the Penn State scientists achieve this? Through ingenious engineering at the microscopic scale. They built a thin film just 2 micrometers thick, made of 5 distinct semiconductor layers. Each layer's thickness and composition was precisely calculated to interact with infrared light. When stacked, these layers create resonances, sweet spots for energy interaction. The real magic happens under a strong magnetic field, which breaks the material's symmetry and enables the violation of Kirchhoff's law. Without the field, the material behaves normally. With it, it becomes extraordinary. The film is transferable. It can be applied to solar panels, computer chips, or spacecraft. This adaptability makes the breakthrough practical for real-world use. To prove their success, the team used a custom spectrophotometer to measure absorption and emission under the magnetic field. The data was clear across a broad range of infrared wavelengths. The material consistently showed strong non-reciprocal effects. They didn't just theorize a one-way street for heat, they built and proved it. The most exciting implications are in energy, especially solar power. Current solar cells lose much energy as heat, radiating it back toward the sun due to Kirchhoff's law. Non-reciprocal materials change the game. A solar cell coated with the 5-layer film could absorb sunlight efficiently, but emit little heat back in the same direction. Instead, wasted heat could be redirected to neighboring cells or devices, boosting overall efficiency. This could dramatically increase solar power output, making it more potent and cost-effective. The concept, energy harvesting, could revolutionize solar farms and reduce the number of panels needed. The potential extends to other clean energy systems like fusion reactors and thermoelectric generators. Materials that absorb heat on one side but prevent emission on the other could create larger temperature gradients, generating more power. This breakthrough gives engineers a new toolkit for next-generation clean energy. It's not just an incremental improvement, it's a fundamental shift in solar and thermal technology. The future of energy just got a lot brighter. Controlling heat flow could transform electronics. Every device, from smartphones to supercomputers, struggles with heat. Traditional cooling, fans and heat sinks, is bulky and inefficient. Imagine a computer chip coated with non-reciprocal material, channeling heat away from sensitive cores and radiating it in a controlled direction. This could enable faster, more efficient computers and slash data center energy use. Batteries could dissipate heat better, improving safety and lifespan. Quantum computers, sensitive to temperature, could use these materials for precise thermal management, accelerating their development. In aerospace, spacecraft face extreme temperature swings. A non-reciprocal skin could absorb energy on the cold side and reflect it on the hot side, passively regulating temperature and saving weight. This technology could also advance infrared sensors and thermal cloaking. The applications are vast, redefining what's possible in electronics, energy, and space. The era of one-way heat flow is just beginning. Challenging a long-standing law forces us to rethink fundamental theories. The violation of Kirchhoff's law has sparked intense debate among physicists. Some see it as a paradigm shift, akin to relativity or quantum mechanics. Others are skeptical, scrutinizing the methods and demanding extraordinary evidence. Replication and further research will test the boundaries of non-reciprocity. Intriguingly, this breakthrough coincides with a quantum discovery. Entanglement can be made perfectly reversible, like an entanglement battery. Both findings suggest we're gaining unprecedented control over energy and information. The synergy is tantalizing. Imagine quantum sensors shielded from thermal noise or ultra-efficient quantum communication. We're at the confluence of two major scientific streams. Breaking old laws isn't the end. It's a new beginning. The landscape of physics is changing, rich with promise for future innovation. We're invited to explore a new frontier. Defying a 165-year-old law is a profound moment in science. The Penn State team's work has opened a door long thought sealed. By demonstrating large-scale non-reciprocal thermal radiation, they've changed our relationship with heat and energy. Reciprocity is now a design choice, not a constraint. The practical applications are vast, super-efficient solar panels, cooler electronics, resilient spacecraft. This is a tangible technological pathway, not a distant dream. The discovery reminds us that science is a dynamic process, always open to revision. Debate and skepticism are strengths, leading to deeper understanding. With breakthroughs in both thermal physics and quantum mechanics, we're on the verge of a new scientific renaissance. Mastery over heat and quantum information could redefine our world. The breaking of Kirchhoff's law is just the beginning of an exhilarating new chapter.